Hello everyone, my name is Abul Mahmoudpour, and in this video we are going to design an anti-reflection coating layer for minimizing of the reflected light from surface of a solar cell. We will utilize the Fresnel equations and will show that by having a very thin layer in the order of several 10 nanometer, we can minimize the reflected light considerably. If you are interested, stay with me. Okay, if you are working in solar cell field, you will definitely find this website very useful. It's pveducation.org. You can find quite fruitful discussion about both optical aspect and electrical aspect of solar cell. Here you see the chapters. In the chapter 5, there is a subsection anti-reflection coating. And indeed, in this video, we are going to show that when we have such a thin layer at the surface of solar cell, we can find the portion of reflected light using this equation. And in the other subsection here, double layer anti-reflection coating, we will see that what if we have two thin layers instead of one with the refractive index of N1, the other with the refractive index of N2, and we want to prove that for this case, the portion of reflected light can be described using this equation. So let's go to the PowerPoint and start our discussion. From electromagnetics, we know that when an electromagnetic wave or light comes to some interface, some portion of this wave will be reflected in general, and some portion of this wave will be transmitted to the second medium. Here we have interface of the first medium and the second medium. The refractive index of the first medium is N1 and the refractive index of second medium is N2. And Fresnel showed that the fraction of the wave that is reflected can be expressed by this equation. R is N1 minus N2 divided by N1 plus N2. And the fraction of wave that is transmitted to the second medium is 2N1 divided by N1 plus N2. But we know that wave contains both information about amplitude and phase. And what we measure in reality is not phase, and it is not the amplitude. Indeed, it is either power or intensity. And we know that the intensity or power is proportional to the square of the absolute value of the wave. Therefore, when we take the absolute value of the wave, and it could be a complex number, therefore it will be some real number. And what we need if we want to calculate intensity or phase, indeed we multiply the wave to its complex conjugate. Therefore, because we measure the fraction of the intensity or power that is reflected or transmitted, we need to calculate this capital R, that is R1, times to the complex conjugate of small r. And this coefficient known as the reflectance. Therefore, what this small little r shows is fraction of the wave that is reflected, and what this capital R shows, this is the fraction of power or intensity that is reflected from the interface. In the same way, the fraction of the light, let's say the fraction of the power or intensity of the light that is transmitted to the second medium, can be calculated using this capital T, and the capital T is this T times to the complex conjugate of itself. And this small t indeed shows the fraction of wave that is transmitted to the second layer. But because we just can measure the intensity or power, and we cannot measure the phase, therefore we are interested to this capital R and this capital T that's known as reflectance or transmittance, and let's call this R and T with Fresnel coefficient. Okay, what if we have two interfaces? We assume that we have three medium. Medium 1 with the refractive index of N1, and we assume that this medium 1 is semi-infinite. And we have some finite thickness of the medium 2 or layer 2 with the refractive index of N2, and the thickness of this layer 2 is D. And again, we have the other semi-infinite medium with the refractive index of N3. Therefore, based on Fresnel equations, we know that let's say Fresnel coefficient of this interface, we define it with R1, will be N1 minus N2 divided by N1 plus N2. And the Fresnel coefficient for the transmitted wave from interface 1 will be 2N1 divided by N1 plus N2. Fresnel coefficient for the interface 2 when waves comes from layer 2 comes from layer 2 and reflected from this interface will be N2 minus N3 divided by N2 plus N3, and R prime 1 indeed is the Fresnel coefficient for this interface when light comes from medium 2 and reflected from this interface. And T prime 1 indeed is the Fresnel coefficient for the transmitted wave when light transmitted from this medium to this medium. Therefore, it will be 2N2 divided by N1 plus N2. Let's assume that we have a wave with the amplitude of unity and the phase is 0. Therefore, what will happen to this wave when it reaches to this interface? Some part of light will be reflected. And what will happen to this wave? The amplitude of this wave should multiple to the R1. And because amplitude is unity, therefore this wave can be expressed just by R1. What will happen to the transmitted wave? The portion of wave that is transmitted from this interface is T1, right? And because amplitude is 1, the wave will be T1. We know that when light travels some distance, it acquires some phase. And this phase can be expressed in the form of exponential of IL. What is L? Indeed, L here I define to be the multiplication of wave vector K2 times to this distance d. And we know that the wave vector is 2 pi divided by lambda at the same medium. And we know that lambda at this medium can be defined by lambda at the free space with lambda naught divided by n2. Therefore, this n2 goes to the numerator. And this phase will be 2 pi times n2 divided by lambda naught times d. Therefore, the wave here will be T1 exponential of IL because it acquires some phase from traveling from here to here. And when, again, light or electromagnetic wave reaches here, some portion will be transmitted. We are not interested now to the transmitted light, and some part will be reflected. Just notice that I just draw the ray trajectory like this to be able to write this coefficient here. Otherwise, because it is normally incident, both are at the same level and we will have the transmitted light and the reflected light at the same level. This is just for driving of the equation. Therefore, what will happen to the reflected light from here? We know that the amplitude should be multiplied to the R2, right? Because we need to calculate the fraction of a reflected wave from this interface. The coming waves is T1 exponential of I2, and we just multiply the amplitude with T1 that we defined here. And when waves again travel the same distance, and the real distance is this one, not this one. As I mentioned, this is just for simplicity for the driving of the equation to be able to write this coefficient here. Therefore, it acquires some another exponential of IL. Here, the amplitude won't change. Therefore, T1, R2, amplitude is the same. And another phase of exponential of IL will be added to this wave. Therefore, in general, it will be T1 R2 exponential of 2IL. Again, some part of this light is transmitted to the medium 1. And we define the transmittance coefficient for the interface 1 when it transmitted from layer 2 to the medium 1 or layer 1. And we define it with, where is it? Yeah, we define it with T prime 1. Therefore, we need to multiply this amplitude with T prime 1. What will be? It will be T1 R2 T prime 1, and phase do not change because we just calculate the wave exactly before and after the interface, and we have not any thickness for the interface. Again, what will happen? Some part of this light will be reflected from this interface. Again, phase don't change, and we need to multiply this amplitude with R'1 that we define to be the reflectance from this interface. Therefore, it will be T1. R2 times R'1 exponential of 2IL. Again, from traveling from here to here, wave acquires some phase. This phase is exponential of IL. Therefore, another exponential of IL will be added. We have the same amplitude, and the phase that is acquired here, again, some part will be transmitted to the third layer, and some part will be reflected. What will be the reflected wave? It will be T1 R2 squared, because another R2 adds from this interface, R'1 exponential of 3IL, this phase added for traveling of this distance, and some part again will be transmitted, and we need to multiply to this amplitude with another T'1, right? And it will be T1 R2 squared R'1 T'1 exponential of 4IL. And the reflected light from here, again, we need to multiply this amplitude with some R'1. Therefore, this R'1 will be R' squared, and the other terms is the same. If we continue it, we can define infinite number of these equations, but we do not need. We just need to derive some of this light that is reflected for the first time. It goes inside, reflected from the second interface, comes here and refracted from this interface, again refracted from this interface for the other reflection, so on and so forth. Therefore, we need to calculate the sum of this wave that in general are reflected from these two interfaces. And when we add this term, this, and this, we have such an equation for, if we define the general reflection for this two interface, we will have R will be R1 plus T1 R2 times T'1 times exponential of 2IL, so on and so forth. I just added this term to each other, and we have this one. And if you notice, we can find some common term here, 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 and here, and this common term is nothing but T1 R2 times T'1 times exponential of 2IL. Therefore, we have only one of this, and if we factor out this common term from this, what will remain is R2 R'1 exponential of 2IL, and here what is remain will be R2 squared times R'1 squared times exponential of 4IL, so on and so forth. And if you notice, you can see that we have some series, right? And we can define this series with this, let's say, compact equation. And when we change m from 0 to the infinity, we will have the first term, that is 1, because any number in power of 0 will be 1. And when m is 1, it generates this term. When m is 2, it generates this term. When m is 3, it generates this term. And from mathematics, we know that such a series will converge to some number, and this number is 1 divided by 1 minus x. Therefore, using of this equation, in our case, we will have R1 plus T1 R2 T'1 exponential of 2IL divided by 1 minus x, and x indeed is this R2 R'1 exponential of 2IL. Keep this equation in your mind, and let's go to the Fresnel equation again for the interface 1 and interface 2. And if you notice, you can see that R1 indeed is minus R'1, or R'1 is minus R1. And if I just multiply this T1 to the T'1, I will have 4n1 n2 divided by n1 plus n2 in power of 2, right? And if I calculate the square of this R1, it will be r1 squared will be n1 squared minus 2n1 n2 plus n2 squared, and the denominator will be n1 plus n2 squared, right? And if I add both hand side of this equation to each other, it will be t1 t prime 1 plus r1 squared at the left, and at the right what we'll have will be this 4n1, because the denominator is common. Therefore in the numerator we will have 4n1 n2 plus n1 squared minus 2n1 n2 plus n2 squared, and 2n1 n2 minus 4n1 n2 minus 2n1 n2 will be remain plus 2n1 n2 here, and we know that this term and this term is same, and it will be 1. Therefore we can easily see that t1 times t prime 1 will be 1 minus r1 squared. And we have the same relation that we derived in the previous slide, and here I just substitute this t1 times t1 prime with 1 minus r1 squared in this equation, and I just substitute, and therefore here in the numerator we will have this term, and in the denominator I just replaced r prime 1 with minus r1, and it will be 1 plus r2 r1 exponential of 2il. And if we calculate the common denominator for the first term and the second term, we will have r1 plus r2 r1 squared exponential of 2il. We have r2 exponential of 2il minus r1 squared r2 exponential of 2il divided by 1 plus r2 r1 exponential of 2il. And we can easily see that this term and this term will cancel to each other, and what is left is r1 plus r2 times exponential of 2il divided by 1 plus r2 times r1 exponential of 2il. And as I mentioned, we are interested to this value, that is r times to the complex conjugate of itself, and we know that when we have a complex number, you can easily calculate the complex conjugate of a complex number just by replacing of I with minus I. Therefore here we will have r1 plus r2 exponential of 2il, and here we will have r1 plus r2 exponential of minus 2il. Same for the denominator, and if you calculate this multiplication, we will have r1 squared plus r2 squared r1 r2 exponential of 2il, right, and r2 r1 exponential of minus 2il. This term, same for the denominator. And if you make it slightly simple by using of the Euler equation, we know that according to the Euler equation, exponential of any complex number can be expressed in the form of cosine and sine, and this is cosine x plus I sine x. And because here we have 2il plus minus 2il, therefore their summation will be 2 cosine 2il, right? And if I substitute 2 cosine 2l instead of this term and 2 cosine 2l instead of this term using of this formula, I will end up with such a equation. Now indeed this is the reflectance from a thin layer when the medium 1 is semi-infinite and medium 3 is semi-infinite. Therefore we have a thin layer with the thickness of d and the refractive index of n2, and we derive the total reflectance as a function of let's say Fresnel coefficient from the first interface and Fresnel coefficient for the second interface. And this Fresnel coefficient, as you see, just are the Fresnel coefficient for the reflection, and there is no term for the transmittance. And we are interested to see, is there any zero reflection, and in other words, can we find the roots of this equation? We can see that this equation is zero only when the cosine 2l is minus 1, right? And if I put minus 1 instead of cosine 2l, it will be r1 squared plus r2 squared minus 2 r1 r2, and we can easily see that this term is indeed r1 minus r2 squared. Therefore R1 will be equal to the R2. And using the definition of R1 and R2 that we have derived or we have defined in the previous slide, we have N1 minus N2 divided by N1 plus N2 should be equal to the N2 minus N3 divided by N2 plus N3. And by multiplying of this to this and this to this, we have these terms. And just by multiplying of left hand side and the right hand side, we will have these terms, and you see that N1, N2 and N1, N2 will cancel each other from the both sides. Also we have minus N2, N3 here and minus N2, N3 here. They also cancel others, and what is left is this, and you can easily see that we will have some N2 squared here minus N2 squared here, therefore it will be 2 N2 squared, and by bringing up this term to the left hand side we will have 2 N1 N3, and finally we can easily see that N2 should be the square of N3 times N1. Therefore, when the refractive index of this thin layer that we have defined is just a square of refractive index of the first layer and the refractive index of the third layer, this equation indeed, let's say this reflectance will be 0. But we have defined another condition that cosine 2L is minus 1. It means that when the argument of the cosine is some integer of pi, cosine 2L could be minus 1. Therefore 2L should be some integer number times pi, that I define this integer number for simplicity with 1. Therefore by using of the definition of this L that we have defined, that indeed is the acquired phase by the wave when it's travel distance d and in the second medium, and it is 2 pi n2 divided by lambda naught times d. It should be equal to the pi over 2. Pi will cancel from the left and from the right, and therefore the thickness of the second layer when is some lambda naught, the wavelength at the free space, divided by 4 times n2, and n2 is the refractive index of n2. Therefore we found the thickness and the refractive index of layer n2 in order to minimize, not say minimize, in order to make the reflected light 0. It means that when the thickness of this thin layer is d, and when the thickness of this thin layer is n2, and they obey from these relations, therefore the reflected light should be 0. Let's just draw this this equation in MATLAB for different wavelengths and define this condition and see will be the reflection 0 or not. Here I did it before in MATLAB, and here you see I think you know this command CLC clear clear all, and I assume that the N1 or surrounding medium, let's say it's 1 air, and N3 is the refractive index of the third layer, and for solar cell it can be approximated with 3.5, although it's different for different wavelengths, but for simplicity let's assume that the refractive index of third layer is N3. And please note that in these 3 layers we assume that there is no absorption and all refractive index are real. Therefore we define that N2 is square of N1 and N3, and when thickness is lambda naught divided by 4 divided by N2, reflection is 0. I defined here, and I'm interested to let's say make reflection 0 for the wavelengths of 500 nanometer, and here 500 indeed is in nanometer. I define some step, and I change this normalized lambda from 1 until 20 with these steps, and this normalized lambda indeed is lambda naught divided by d. Therefore what will be the L? It will be 2 pi n2 divided by normalized lambda. Where is L? We have defined here, yeah. This is L. I defined this normalized lambda with lambda naught divided by d. Therefore it will be 2 pi n2 divided by normalized lambda. And I defined R1, that is N1 minus N2 divided by N1 plus N2. I defined R2 here, N2 minus N3 divided by N2 plus N3. And this is the same relation that we have derived here. I just wrote exactly the same equation. And here I plotted this reflectance versus this wavelength, that is normalized lambda multiple to the d. Normalized lambda multiple to the d will give us the wavelengths. And indeed, because I'm changing the normalized lambda, I'm changing the wavelengths. Therefore, let's see, do we have zero reflection at the 500 nanometer when we have defined this condition for the refractive index of the second layer and for the thickness of the second layer? By pressing of F5, you see the plot for the reflectance at different wavelengths, and I just plotted two a vertical line, one as at 380 and the other is at 700. That is shows the visible spectrum, and you see that we have zero reflection when the wavelength is 500 nanometer. And just if you are, for example, want to make minimum reflection at the 400 nanometer, if you put 400 here and press F5, you see that we have again zero reflection, and the value for N2 is 1.87. and the value for D is 53.4. You can see the same row here, and you see that by changing of the refractive index of second layer, you see how reflectance changes, and by changing of the thickness, you see how does it change. And you see that what we found for 400 nanometer, if we want to be zero reflectance for 400 nanometer, N should be about 1.9. Let's adjust refractive index to 1.9. It's exactly how much it is. 1.87. 1.87. And what should be the thickness? The thickness should be about 53.4, and here by reducing of the thickness to the 53, we have zero reflection at 400 nanometer that we derived exactly the same graph. And here in this red line here, when the ambient medium is air, and it is exactly the same blue line that we have drawn here, and here indeed is the same equation that we have derived. Let's go to the next part and try to derive the part of, let's say, power or intensity that is reflected when we have double layer instead of a single layer. Now we have two thin layers with the thickness of D2 and the refractive index of N2, and the other thin layer is with the thickness of D3 and the refractive index of N3, and the semi-infinite layer, first semi-infinite layer with the refractive index of N1, and the semi-infinite layer for the fourth layer is refractive index N4. So the question is, do we need to do the same ray trajectory that we have did in the previous slide? The answer is no, because if even it is possible, it will be mind-blowing. You need to find the waves start from here and try to find the reflection here, transmittance here, reflection here, transmittance here, and again for transmitted reflected light from here, you need to find transmittance from here and reflectance from here, and the same light from again here, transmitted from here, reflected from here. It will be really complicated, but the solution is very simple. We have derived for one thin layer. What if we assume that this layer 2 is semi-infinite and we start calculation from here. Imagine that we have a lights here, and lights comes from here, and let's find the reflectivity from, or reflection coefficient from the interface 2 and interface 3. We did it in the previous section, and we know that if we define it with R23, it will be R2 plus R3 exponential of 2IL3 divided by this, and L3 here is 2 pi N3 divided by lambda naught D3, and R2 should be N2 minus N3 divided by N2 plus N3, and R3 should be N3 minus N4 divided by N3 plus N4. Now that we know the total, let's say, reflectivity from this thin layer, we can squeeze this thin layer and define it with some interface that the total reflectivity is R23. Now what we have two interface R1 and interface R23, and we have N1 here and N4 here, and the refractive index is N2. This time again, what will be the total reflectance based on the previous results? If we define it with R, it will be R1 plus R23 exponential of 2IL2 divided by 1 plus R1 times R23 exponential of 2IL2, and again this time L2 will be 2 pi N2 divided by lambda naught times D2. R1 is N1 minus N2 divided by N1 plus N2, and we see that R23 should be this one. Therefore we have this equation and this equation, the same equations, and by substituting of this into this, what we have R should be like this. What I did, I just substitute this here, and by calculating the common denominator for the numerator and denominator, then this term will be cancelled this term, and what is left is this R1 plus R1 R2 R3 exponential of 2IL3 plus the same terms R2 exponential of 2IL2 plus R3 exponential of 2IL3 plus L2, and same for the denominator. And what you need, again, you need to calculate this coefficient. This times to the complex conjugate of itself, and if you do this here, you have 4 term here, 4 term here. Therefore, in general, in the denominator, you should have 16 term, and you can easily check what we have. And for example, here we have R1 squared, that is here. We have R1, R2, R3 squared, that comes from, it comes from this, and R2 squared, so on and so forth. Just simple mathematical calculation. If you do this calculation, you will get this equation. And again, by using of the definition of Euler equation and substituting of cosine to L2 instead of 2 cosine to L2 instead of this term, and similar for the other exponential term, what will you get? You will get this equation, and just after some resorting of this term, you can easily check that this term is exactly the same term that you saw in the website of pveducation.org when we have two thin layer. Just it's a simple mathematical calculation, and you can easily control everything here. Yes, and let's go to the MATLAB again and try to draw the same. And I did it again before. Here, let me. Okay, come here, and I just enable this commands with Control T. Why it doesn't respond again? Okay, again, N1 is 1, this time N4 is 3.5, and let's define N2 with 1.35. And just if you notice to the equation that we have derived here, you see that this time it is not very easy to find the roots of this equation. Therefore, it is what you can do, just try to draw it and try to change the thickness and the refractive index, and to see how reflection changes, and can we have any minimize or zero reflection for too thin layer or not. And okay, here therefore I have defined N2 with 1.35, N3 with 2.48, D2 100 nanometer, D3 55 nanometer, and here I changed lambda from 200 until 1200 nanometer with the step of 1. Therefore, definition of L2 will be this, and definition of L3 will be this, R1, R2, R3. Sorry, and this is the numerator of the equation that we have derived. You can check, and this is the denominator of the equation that we have derived. Therefore, all, if we want to express it in the percent, it should be 100 times numerator divided by denominator, and I just draw the R versus of lambda, and let's put it again to 500, and by pressing F5, indeed this blue curve shows the reflectivity for single layer, and this red curve shows the reflectivity for the double layer when the reflection, when this let's say refractive index value for different layer is like this one, 1.35 for the second layer, 2.48 for the third layer, and 3.5 for the fourth layer. And you see that by utilizing of two thin layers instead of one, you can easily increase, let's say, the bandwidth of the zero reflection. And you can again just check this graph with the graph that exists in the website. Just for comparison, let's define N1 is 1, N4. We just need to change N2 and N3. N2 should be 1.35. N2 should be 1.35. Here is indeed N2. This one is for second layer, and this one first thin layer, and this one is for second thin layer. Therefore, 1.35, right? Okay. 1.35 for N2 for first thin layer, 2.48 for second thin layer, 2.48, 2.48, and 100 nanometer for the first thin layer, and 55 nanometer for the 55 nanometer in okay here for the second thin layer. And you can easily see that this red graph is exactly the same, red here, and this is for single layer and this is for multi-layer, and you can check this equation with what we have derived by using the calculation that I showed you. I hope you have enjoyed this video. If yes, do not forget to like the video and share it with your friend. Thanks you for your attention.